Okay, today I will talk about the Skew curvature flow. I'm sure yesterday Professor Cassian must have talked about it a little bit, which I missed, unfortunately. So we will start from a bit introduction, and then I will introduce main results and some open problems. And then finally, I will briefly introduce the idea of proof. So let's start with the formal definition of a Skew curvature flow. The so-called Skew curvature flow, or sometimes simply binomial flow, is a geometric evolution equation which involves a codimension 2 submanifold along its binomial direction and with a speed given by the mean curvature. So formally, for a family of submanifolds F, let H denote its mean curvature and J denote the complex structure on the normal bundle, which simply rotates a normal vector by pi over 2 in the normal plane positively. This positivity is, of course, given by the orientation of the submanifold and the ambient space. Okay. This Skew curvature flow can be defined in any Riemannian ambient manifold and for any dimension, as long as the submanifold is of codimension 2. This is, of course, very similar to the famous vortex filament equation. I believe there are many experts on this topic, but let me briefly recall. So for the one-dimensional Skew curvature flow in R3 is just the vortex filament equation, because in this case, the submanifold is of dimension 1, which is a curve. And at each point of the curve, we have the normal plane, and we have the Frenet frame. So the equation is just gamma t equals kappa b, where b is binomial vector and kappa is a curvature. There's a beautiful transformation called the Hashimoto transformation, which transforms the vortex filament equation into this cubic Schrodinger equation. From a geometric point of view, this Hashimoto transformation amounts to rewrite the evolution equation of the curvature vector in a suitable frame of the normal bundle. Okay, so at the second row, the classic vortex filament equation is written in the Frenet frame, but you can, of course, choose other frame of the normal bundle, and you can derive the evolution equation of the vector curvature vector. So if you can find a frame along the curve of the normal bundle, which is parallel along the curve, okay? And then you express the curvature vector in this modified frame, then you can naturally get the cubic Schrodinger equation, okay? This vortex filament equation is completely integrable since the Schrodinger equation is. So it has rich structures. In particular, it has infinitely many conserved quantities, and it has soliton solutions. Here, by soliton, I mean the curve evolves along the flow without changing its shape. So it can, in R3, it can translate or rotate. Here I give some of the well-known Soliton solutions. The first one is a circle, which is translating Soliton, and the helix is also translating, and the rest two are rotating. They will rotate along the axis. And figure 8 is a closed one, and wave-like is not closed. And interestingly, these Soliton curves are closely related to Euler's elastic curves and the so-called magnetic geodesics, which models the movement of particle in a magnetic field. There are also there are very few explicit examples for high-dimensional Skew culture flow, but Cassian and Young recently gave a very beautiful example, which is simply a product of spheres. So suppose we have a product spheres of m dimension and n dimension, which are embedded in Rm+1 and Rm+1 respectively. Then you can run the flow, and as a result, the product structure will preserve. The only thing that evolves along the flow is the radius of the sphere. And we have very simple equation of the evolution. And in particular, when the spheres are of same dimension, then the flow exists globally. And as you can see, the radius evolves as a exponential function on time. And one of the radius is shrinking while the other is expanding. But they all go to infinity, and at time infinity, it will shrink to a line actually. And when the dimension is different, for example, the most simple example is S1 times S2 in R5, then actually the flow will blow up in finite time, which is, I believe, the first non-trivial example of finite time solution to high-dimensional Skew-Kirchhoff flow. So other than that, actually, we don't have explicit examples, because if the initial data is not a circle, then it will easily get messed under the evolution. Okay, it will no longer stay in the hyperplane. Okay. So where does this Skew-Kirchhoff come from? Of course, it has the same origin as the vertex filament equation, which comes from the study of the Euler equation. And it was first discovered by Darius over 100 years ago. But the higher dimension analog is only discovered up to 2000. Okay, first it was derived by Xiamen in 2012 for 2D, and then Cassian generalized it to any dimension. It also arises from the study of vortex in superfluid. For example, the Gross-Pitevsky equation, which models the wave function of Bose condensate. There's a conjecture which is parallel to the vortex filament conjecture, of course, which says the vortex is if the vortex is concentrated on a codimension 2 submanifold, then under this Gross-Pitevsky equation, it will evolve along the vortex subset will evolve along the Skew-Curvature flow. I believe it was first solved for 1D studied for 1D vortex filament by Lin in 2000, and Gerard solved this problem for when the vorticity concentrate on a sphere with multiplicity 1. And actually, besides this Schrodinger type Gross-Pitevsky equation, there are similar structures for parabolic PDEs and hyperbolic PDEs, which arise in different contexts of physics. So my research focuses on geometric analysis. So I'm interested in this flow because it's closely related to other geometric flows. One way to view the Skew-Curvature flow is to regard it as the Hamiltonian flow of the volume functional, which is defined on the infinite dimensional symplectic manifold. So the manifold is the space of all possible inversions of a given underlying manifold. Okay, and we have the so-called Marsden-Weinstein symplectic structure. And if you consider the volume functional as a functional defined on this symplectic manifold, and then you can study its Hamiltonian flow, which is exactly the Skew-Curvature flow. And actually, the well-known mean curvature flow is just the gradient flow of the volume functional. So the Skew-Curvature flow can be seen as the Schrodinger counterpart of the mean curvature flow. And if you look at the Gauss map of the Skew-Curvature flow, then you can find that it satisfies the another famous flow, which is the Schrodinger map flow. Okay, so it's a Schrodinger type equation, but it involves a map between manifolds. Okay, so the Gauss map of a submanifold is a map from the underlying manifold to the Grassmannian manifold of the target or the ambient manifold. And if you choose the ambient manifold to be Euclidean, then the Grassmannian manifold is very simple. It's not a bundle. Sorry. Oh, whoops. Okay. And interestingly, this Grassmannian manifold has a natural, canonical Kähler structure. So the Gauss map now becomes a map into a Kähler manifold. And this Kähler manifold has a canonical complex structure, which is denoted by JG here. And the equation of the Gauss map rho is like this, okay? So this is known as the Schrodinger map flow. But here there's a difference from the Schrodinger map flow, the classic Schrodinger map flow, because here this underlining, this G is the induced metric, okay, given by the immersion of the submanifold. So as the submanifold evolves, this underlining metric also evolves a long time. And actually you have this equation of the evolution of the metric. So it's more difficult than the traditional Schrodinger map flow where the underlying metric is fixed. So actually this equation does not live alone. It's kind of a coupled system with this evolution equation of the metric. And it is well known that the Gauss map of a minimal submanifold is harmonic, and also the Gauss map of the mean curvature flow, okay, which is parabolic, satisfy the harmonic map heat flow. So actually, I have this little table of which I want to explain the relations between different flows. So here I mean the type of the equation. Okay, so you can consider classic elliptic type equations or heat equation or wave equation or Schrodinger equation. And if instead of functions, you consider mappings between manifolds, then you have harmonic map heat flow, and wave map and Schrodinger map flow. Okay, and here, if you consider the geometric flow, which involves a submanifold, then you have the static one, which is a minimal submanifold, and you have the parabolic mean curvature flow, and you have, actually there are some investigations of hyperbolic curvature flow, but there are several models, and the research has just started. And here we have this Schrodinger type evolution, which is the Skew mean curvature flow. And in the bottom line here, I mean the corresponding energy functional, okay? And the relation is this. So as I explained in the previous slide, if you consider the Gauss map of the geometric flow on the third column, then the Gauss map of this column will satisfy the second column, okay? Will become a map. Here we have the corresponding equations. And here, if you consider the Ginzburg-Landau energy functional and the corresponding equations, and you consider the vortices, okay, possible vortices which are concentrated in some submanifolds, then the submanifold will satisfy the evolution equation of the third column, which is very interesting, okay, and mysterious. Okay, so as you can see, there are many rich background about the Skew mean curvature flow, but I'm concerned about the initial value problem. I want to know, given a submanifold, how does it evolve along the Skew mean curvature flow? So the basic problem I have to answer is that can this flow start? Okay, if it can start, then how long can it go? And if we are fortunate enough, could it exist globally? And what's the asymptotic behavior of this geometric flow? Okay. So unfortunately, this problem is very difficult. And after years of investigation, I can only solve the local existence and uniqueness problem. And there are many problems left wide open. Okay, so so next, I think I'm going to talk about some analytic aspects of this flow, and mainly concerned with its existence.
Hello?
Chong, your connection seems to have cut out. Can you still hear us?
Yes, I can hear you. Hello?
Okay,
Hey,
yeah, if you
so
could
we
repeat the
can't
last
see-
phrase.
Yeah, we
Oh.
can't see your slides anymore. Are you able to maybe stop
Oh.
sharing and then share them again?
Okay,
No,
okay,
no.
let me try.
Sometimes I can reset it.
Can you see my screen now?
Can people see Chong's slides? I can't. So I'm not sure if others can. I assumed others
Oh,
can't.
I'm terribly
But
sorry.
I can't.
okay, yeah, so we can't see your
Oh.
slides.
Okay, let me try again.
Yeah, try one more time. And then if you can't, are you open to maybe sharing your slide deck? Like, are you able to send me the PDF of your slides?
Oh. Now I'm sharing again. Can you see it?
No, we can't see your slides.
Oh.
So are you able to send your slides or post your slides in the chat here to us?
Sure. But,
If you're able to do that, I'll see if I can open your slide deck and then I can run your slides for you. So let's see
okay.
if we can do that.
How can I send the file to you?
If you go into the chat, there should be a button at the bottom of your screen that says chat. So, or something like chat. If you're able to press on that, you'll see a space where you can type to people. And there's a button there that should say file. So if you're able to click that, you should be able to send your file to all of us of your slides. If it's easier, you can email them to me at this address.
Okay,
I'll
I sent
just,
this
you
file.
sent it?
Can you see? It's uploading.
Okay.
But you can hear my voice.
Yeah, we can hear your voice and we can see your video
great.
just fine. So, okay, here's your slides. Let's see. Let me download them and then I'll run the slides.
Okay.
No worries, I will add several minutes, no problem.
It happens. It's okay. No problem. Let's see.
Now, by the way, we see you again, so you might
okay. Let me try again.
Yeah, maybe it will work. Let's see.
Can you see it?
Not yet. I mean, it's working on that.
I've got your slide deck open as well, so if you'd like me to run your slides, I can do that.
So you still cannot see my screen?
No, we cannot see your screen. Yeah, it's just working and working and working.
Okay, okay.
Okay, so here's your slides. And can you, so can everybody see the slides now from my screen?
Yes, I can see.
Okay,
great.
Yes.
I just, you'll have to remind me what slide you were on. Can you let me know when to stop?
Go on.
It's
here.
Yeah, it's here.
Okay, perfect.
Just
So
one back. I
Last
think,
page.
Oh,
Just
the last page?
previous one.
That one?
Yeah. Here.
Okay,
Yes.
perfect. So just let me know when you want me to advance the slides and I'll move them ahead for you, okay?
Okay, thank you very much.
Yeah, no problem.
So as I was saying, so I want to study, I want to see the structure of this equation clearly. So first I can choose a local coordinate around some point, and then in that local coordinates, we can write the mean curvature vector like this, which is well known in it's just basic geometry. So as you can see, this curvature actually involves with the first and second order derivative of f. In particular, the metric depends on the first derivative, tf, and the complex structure also depends on the first derivative, but the Christoph symbol depends on the second order derivatives. So this mean curvature vector, although I denote it by a simple symbol, but actually it's quite messed up. And actually you can see more clearly if we assume this F to be a graphic solution. Here in the last line. So F of X, where X is denotes a variable in the n Euclidean space, and we suppose that the action of F will preserve X while it has a graphic representation of phi. Since it's codimension 2, so we have two functions, phi1 and phi2, then you can write down a complex valued function with components given by phi1 and phi2. Then this phi will satisfy such a Schrodinger type equation. However, it's highly nonlinear, because you can see the nonlinear term involves the second order derivatives and also the first order derivatives. So here I only write down the leading order term. Actually, we have many other terms. So as you can see, it's highly nonlinear.
Next slide.
Yeah, next slide. Thank you. So first, we can recall the global existence, the existence results of 1D Skew culture flow. I believe this problem has been studied by many people, but here I only quote one, which I think is very general. So Gomez proved that in any three-dimensional Riemannian manifold, if you consider a smooth initial curve, which has L2 bounded curvature, then this 1D Skew culture flow has a unique smooth global solution. And his proof actually used the Hashimoto transformation, and instead of doing analysis on the Skew culture flow, the flow equation itself, he actually did the estimate for the transformed Schrodinger equation. Okay, and it can work because the induced metric on the curve is static. It does not evolve, unlike the higher dimensional case. And actually, if you do not assume the bound on the curvature, there are smooth initial data, initial smooth curve, which can develop singularity in finite time. Professor Weger and his collaborators has done many works in this direction. So next slide, please. So for higher dimensional Xiamen curvature flow, it's a totally different picture. Because the key difference, as I had mentioned, is for dimension larger or equal to 2, the underlying metric is evolving a long time. So it becomes a very complex nonlinear Schrodinger system, and it's not covered by any existing theory on nonlinear Schrodinger equations. And the familiar geometric analysis trick, the deterb trick, does not apply. And it seems there's no Hashimoto transformation for dimension 2, which is investigated by Cassin. So it's not likely. So I don't believe personally it's integrable. So apparently the only preserved quantity is the volume, and I can't find any conservation laws. And it's more difficult to prove the uniqueness, because for a nonlinear Schrodinger equation of this form, which is simpler, much simpler, okay, the uniqueness is also very difficult, and has many, the existing results always requires very restrictive structures. Okay, next. So here, so my results towards this direction. So several years ago, I and Sun proved the local existence of 2D Xiamen curvature flow, which is defined for a smooth initial compact surface. Here, compact I mean closed without boundary in R4. And we only proved the local existence. But we find that the existence time, the maximum time, only depends on the subleft norm of the second fundamental form A, and also the volume. And we use the technique which is only works for dimension 2. Okay, next. So last year, I proved that for any n-dimensional smooth initial compact submanifold in Rm+2, we have local well-postness. Here I proved existence and also uniqueness. And the exist time depends on some subleft type norm of the Gauss map. And actually this norm is equivalent to the bottom line to the volume plus LP norm of the mean curvature and the subleft norm of the second fundamental form. And actually, we only did the Euclidean case, but we can actually, with some subtle work, we can extend this result to some more general data and more general ambient manifold instead of Euclidean space. Okay, next. And the study has just begun. I only got studied the local existence and uniqueness. So there are lots of open problems, which is really hard. So first, I want to know about the regularity. So I think our assumption on the initial manifold is not optimal. So one might want to know about the optimal regularity for existence and uniqueness. And we don't know the existence for non-compact submanifolds. And Professor Cassin has given a simple finite time solution, but it's in R5, so it's a 3D example. So I want to know if there are 2D finite time solutions. And also, it's very common for Schrodinger type equation that we have global existence for small initial data. And the most interesting problem perhaps is the long time existence and the long time asymptotic behavior of this flow. Because once you have some clue of this long time behavior, then maybe we have some interesting geometric applications of this flow. Just like we can use mean curvature flow to find minimal submanifolds. And also, we want to know, is there any solitons? As you can see, we can classify the 1D solitons of the vortex filament equation, but we actually don't know any non-trivial soliton for higher dimension, which evolves without changing its shape under the Skew mean curvature flow. And if there's such a soliton, it would satisfy such an equation. Here, J is complex structure, H mean curvature vector, and K is some given Killing vector fields of the ambient space. Okay, next. And recently, I'm happy to see that there are some progress for some of the open problems. First, Dizhe has studied a simple case, which is a graphic submanifold. So a graphic submanifold is just a transversal perturbation of the hyperplane, codimension 2 hyperplane of the Euclidean space. So he requires the perturbation is small in some subleft space. Then he can prove there is a global solution. And also Huang Jiaxi and Tataru from Berkeley has studied the local web postness for non-compact submanifold and also got some impressive results. Here, I think their requirements on the regularity of the initial data is almost optimal, but they only get local web postness. Okay, next. Yeah, next. So here I will. So I have 7 minutes. So maybe I will rush on the existence part, and I will mainly introduce the idea of the proof of uniqueness, because the uniqueness is more difficult. So if the existence is proved by a rather regular method. So we don't have a existence theory for nonlinear Schrodinger type equation. So we perturb this equation by adding the mean curvature. Okay, then this perturbed equation becomes a parabolic type equation. It's weakly parabolic actually, but we can use the well-known Dirac trick to translate it to a strictly parabolic one. Then one has a local solution, automatically has a local solution for this perturbed Skew mean curvature flow. Then we will let the perturbation go to 0 and try to derive some uniform estimates, which is independent of this epsilon. We will use a energy method. So the strategy is really regular, but it's easier said than done because you can you don't know what kind of uniform estimates you can get. So next, please. First, here's a table of evolution equations of different geometric quantities along the perturbed flow. And then next. The key problem here is that the underlying metric is evolving. So if you want to use energy method, you will need to use the Sobolev inequality. But the Sobolev constant depends on the underlying metric. So that's a problem. But fortunately, we have this kind of uniform Sobolev inequality, which is where the constant is independent of the metric. But we were to use such type of uniform Sobolev, we will need uniform bonds on the volume and LP norm of the mean curvature, where P is larger than the dimension. So as long as we need this bound of the volume and mean curvature, I will directly put this volume and this LP norm of the curvature into the energy. Okay, next. And the next, please. Yeah. So I will just put the volume and the LP bound of the LP norm of the second fundamental form into this energy, and try to derive a Gromov type equation for this energy. Or in other words, I want to show this energy is locally bounded for the perturbed flow. And the bound is independent of the perturbation epsilon and only depends on the initial data. So once you find this, the correct energy, then this could be done easily. Okay, next. Next, please. So the really technical part is the uniqueness, because as I said, even the uniqueness problem of a much simpler Schrodinger type system is difficult. So suppose we have two solutions of the Xiamen creature flow, then we need to prove that these two solutions are actually identical a long time. So here again, I will use energy methods because we do not have maximal principle. We do not have pointwise estimates. But the key problem is that if you try to, so usually you will directly compute the difference of these two solutions. So maybe you want to try to compute F minus F tilde, but that will never work because this difference is too rough. You need a more precise way, a more intrinsic way or optimal way to do the difference. So I will use, here I use the a very important geometric idea, which is simply the parallel transportation. Okay, next. Ooh. So uniqueness. And next, go on, go on. Go on, please. Okay, yeah, here. So let's first recall how can we compute the difference of two vectors on a given manifold. So suppose we have two vectors. One is the vector on X, another is capital Y, which is a vector on Y. So one way to define the distance or difference of X and Y is to embed this manifold into a larger Euclidean space. Then you directly see X and Y as vectors in the Euclidean space, then you do the difference. But it's not a canonical way to define the difference of X and Y. So intrinsic way without embedding M into a larger Euclidean space is to find a geodesic between the point X and Y, and then parallel transport one of the vectors, say Y, to the tangent space of X, and then to define the difference of X, Y by compute the difference of X and the parallel transported Y. Okay, so now they are in the same tangent space. You can define the difference. So that's a very simple idea. Okay, next. But here, we are not dealing with simple vectors. We are dealing with two submanifolds. So the most important geometric quantity of the submanifold is its second fundamental form. So we want to apply the idea of parallel transport to define the difference of different second fundamental forms of different submanifolds. So how can we do that? So a key observation is that the second fundamental form can be viewed as the tangent or the differential of its Gauss map. Okay, so the second fundamental form can be viewed as a tangent vector, some type of tangent vector on the Grassmannian manifold. Okay, so we will use the parallel transport to on the Grassmannian manifold to define the intrinsic distance of two second fundamental form. Okay, here I use the letter D1 to denote the distance defined by using parallel transport. So I defined the difference of second fundamental forms by using by the distance of the differential of Gauss maps, which where I use the parallel transport. Actually, we can not only define the intrinsic distance of a second fundamental form, we can actually do better. We can define the intrinsic distance of any tensor of the submanifold by using such an idea. Okay, as my time is out, I will omit this. Please go to next page and next. Yeah, so I will use the immersion and the parallel transportation of the Gauss map to define not only the distance of second fundamental form, but also of any type of tensors defined on two submanifolds. Okay, next. So finally, I find energy functional to describe the distance of two submanifolds, which is given by a very complex integration. So it involves the distance of Gauss map, the intrinsic distance of second fundamental form, and also the derivative of the second fundamental form, and also other lower order terms. So once you find this energy functional, then you derive the evolution equation of this functional, and we will get uniqueness. Okay, I will stop here. Thank you.
Thank you very much.